Good morning, students.
Good morning.
So, okay, yeah. Today we will discuss about some applications of solar cell. In last class, we are discussing about the working and construction of the solar cell. Okay. Yes, am I audible, students?
Yes, sir, you're audible.
Last class we discussed about the uh, so that means how working, so construction of solar cell we will discuss, and principle of the solar cell we will discuss. Okay, today we will discuss about the some application. Before going to the just I will give brief introduction about what we discussed in last class. Okay, yeah. Okay. Uh, so in last class we discussed about the construction. Here if you see the construction of the solar cell, that means here we can take initially either N-type material or P-type material, whatever it will be there. Okay, so initially we will take either N-type material or P-type material. On that, if you will take P-type material means on that we can grow on N-type material. You can grow on N-type material. So if you dope the N-type material here, so what happen in between, there is a so some band will be takes place, the depulsion region will be takes place due to the diffusion process, and so there is a one more shield will be there, so that is the transparent conducting film. So it protect the total solar cell. It will protect the total solar cell. Okay, whenever light is instant on that, so it allows that conducting film is allows to the light into the this. So that means that whatever light will be there, that light is fall on the either P-type and both, so P-type and N-type materials here. Okay, so after light illumination, what happened here? So covalent bonds will be breaks. And in that P region, so here covalent bond will be breaking means here electron hole pair will be generated. Electrons will move towards to the this region, and electrons are accumulated here. Similarly, holes are accumulated here. Okay, there is a see here. So that means from P region, electrons are moving from P region to N region. Similarly, holes are moving from N region to P region, and those are accumulated at the boundaries, at the junction, not boundary, at the junction. They will be accumulated at the junction of P and N region. Okay, due to this accumulation, what happened here? Some potential difference will be developed. So due to that potential difference, what happened? Current will pass through the circuit. So if you connect the load resistance, so we can take the output from through that load resistance. Okay, so that means which type of resistor we have to use here. Okay, so that means based on the IV characteristics, of solar cell, we can decide so which type of resistor, that means how much how much ohms resistor we have to use. Okay, generally in case of silicon materials, generally 4 ohms material will be used. 4 ohms resistor will be used. Okay, 4 ohm in case of general that means solar cell made with silicon. Okay, so generally they will use 4 ohm resistor. 4 ohm resistor, it gives the approximately 0.6 volts. 0.6 volts. Okay, So that is voltage is not important for us. So power is main important. So power is main important. So based on that, so how to calculate the power means P is equal to V into I. So based on this IV characteristic diagram, so we can calculate the at which point. So that is the power maximum. Okay. So if you draw the curve here, yeah, I will. So if you draw the curve between the power versus voltage, so that curve will be that power is increasing with respect to the voltage, so up to a particular value. So here only after that, so that power will become suddenly reaches to the zero. Okay, that's why. So this is the at this point we will get the maximum power. So at this point means corresponding current. So what is the corresponding current? Im and corresponding Vm. How to we will get this corresponding Im and Vm means, so based on the which type of resistor we are using here. So that means how much ohms resistor we are using here. Okay. So based on that resistance, so we can control so that means while changing the resistance, what we have to do? So we can change the we can change the voltage here. Okay. So while changing the resistance, so we can change the voltage here. So if you increase the resistance, so voltage also increases. So that current will become slightly decreases up to particular value. After that, current will become drastically zero. Okay. So at which point sufficient current and sufficient voltage will be present. At which voltage sufficient, sorry, at which resistor sufficient current and sufficient voltage we can gain. That resistor we will use as a load resistor. Okay. So based on this load resistance, so output power will be depends on. Okay. So this is the IV characteristics here. And so by using this current equation, total current equation in a solar cell, this is the total current passing through the solar cell here. So by using that equation, we can based on these conditions, already I said that at a 0 volt, so at a zero voltage, that means without load resistance. So what is the current passing through the diode? That is the maximum current. So that is I short circuit current. Okay. So that is the maximum current passing through the circuit. That is the ISC. Okay. Similarly, if you will take VOC. Okay. Now, so how already I explained you how to calculate the ISC and VOC. So VOC is nothing but here. So no current passing through the diode. If there is no current, passing through the solar cell, so voltage is called as maximum voltage. So that voltage we will call it as open circuit voltage. Okay. So how to calculate this means, so now first of all, if you want to find out the short circuit current, ISC, so how to calculate the ISC means, just remove the load resistance and connect these two terminals. Here one terminal will be there, here another terminal will be there. Just remove the load resistance and connect those two terminals. Okay. Then we will get the here. Yeah. So we are just removing the load resistance and we are joining these two terminals here. Okay. If you join these two terminals means, now what is the current passing through the circuit? That is the ISC. Okay. Without load resistance, what is the current passing through the circuit? That is the short circuit current. Okay. By experimentally how to measure means, so just remove the load resistance and short these two terminals. Now by using ammeter we can measure the current passing through that is the ISC. Now coming to the VOC. So VOC means, just remove this total connection. So total connection, and so just we will place the voltmeter in between these two terminals. So just by using voltmeter here, so and we have to remove this total connection. Just place the voltmeter here. So now, so what is the voltage across the diode? So that is the open circuit voltage. Open circuit voltage. Okay, this is about the short circuit current and open circuit voltage. Okay, now so by using different resistors, so we can vary the voltage. So by varying the voltage, so current will be changed through the circuit. Okay, so if you draw the graph between so voltage versus current, that graph will be like that. So at a particular point, so power will be maximum. P is equal to V into I. If you multiply the so V into I, we can get the power. Okay, so if at a particular value of the I and V values, so power will be maximum. Those values are Im and Vm. So that resistor, that corresponding resistor is the so load, we can use it as a load resistor. That point, these points we will call it as operating points of the solar cell. Okay, now how to calculate this ISC and so V0 VOC. Okay, so see here. Uh, Already we know that this is the total current formula. I is equal to I naught into EV by e power EV by KT minus 1 minus IL. Here IL is the current passing through the load resistance. Current passing through the load resistance. I naught is the reverse saturation current. Reverse saturation current. Okay. Now suppose if V is equal to 0. If V is equal to 0. Okay, so if you substitute V is equal to 0 here, so we will get the ISC max. That means short circuit current. Okay, so ISC is equal to minus IL. Okay, this term will become vanishes if whenever if you substitute V equals 0. So e power 0 means so that equal to 1, 1 minus 1. So this total term will become 0. Okay, now so for calculating the VOC, so what we are putting for calculating the VOC, just we have to put the I is equal to 0 here. I equal to 0 in this above equation. Okay, if you put I equal to 0, so now if you simplify it, e power EV by KT is equal to 1 plus IL by I naught. Okay, what we are doing here, just putting V is equal to VOC. So instead of V, we are putting VOC, and here so there is E by KT, and KT, that means KT by E. KT by E is the thermal energy. Okay, so instead of KT by E, just we wrote the VT. Okay, now if you substitute that, so VOC. So this is the equation for so open circuit voltage. Open circuit voltage. Simply we can write so VT is equal to ln of IL by I naught. Okay, this is the open circuit voltage. And power. We know that formula, power is equal to V into I. V into I. So this is the equation for power. This is the equation for power. Okay, now so what is the maximum power condition? Maximum power condition means, so if power will become maximum, if power will become maximum means if you differentiate it, that will be a 0. That will be a 0. Okay, so that means dp by dv. So by differentiating this power value, we can calculate the Vm and Im. Vm and Im. Okay, so no need that calculations. This calculation is not required for you. Okay, not required for you. Okay, in exam also no need to write this calculation. Okay, they will ask just about the solar cell IV characteristics. Then didn't ask so this so calculate the Vm and Im values, maximum power point values. They didn't ask. Okay, that's why no need to calculate the this so Vm and Im values. Okay, coming to the solar cell materials. Solar cell materials. Okay, so here previously we discussed about by using N region and P region, so we can prepare the N type semiconducting material, P type semiconducting material. We can prepare the solar cell. Okay, which type of material we have to use? So we can use for preparing the solar cell material. Yeah. Here generally we will use the monocrystalline silicon material. Monocrystalline silicon. Monocrystalline is nothing but single crystalline silicon material. Because why we are using this monocrystalline silicon material means silicon is cheapest material in the earth. Silicon is the most available material as well as cheapest material in the earth. Okay, that's why. So if you use monocrystalline silicon material means so that solar panel will be very cheap, very cheap. But efficiency compared to other materials, this efficiency will be less. Efficiency will be less. Okay, So general so bulk production of solar powers, bulk production of solar powers. So generally we will use it as a silicon, because for bulk production we need so much of large material. Okay, so if you will take high costly material, means it will be very that means efficient, very costly. Okay, so that's why we cannot use so other type of materials in case of bulk materials. So bulk solar panels, so generally we will use it as a monocrystalline silicon, because so this is the cheapest material. Okay, so one more also there, that is the hmm, so this is the crystalline material. Another one also there, that is the amorphous silicon. So amorphous silicon material also we can use. Amorphous silicon material also we can use as a solar panels. So what is the difference between monocrystalline and amorphous? So what is the difference between crystalline and amorphous? Anyone knows that? So crystalline is nothing but, if you will take so one material, silicon material, here in that silicon material atoms are oriented in a periodic manner. So atoms are, so if you will take any material, that material is constructed by so many number of atoms. Okay, so that means crystalline is nothing but, so those atoms are oriented in a long range periodic order, long range periodic order. Okay, so if you will take amorphous materials means that long range order will be breaks. Okay, so that means those atoms are oriented randomly. There is no long range periodic order. There is no long range periodic order in amorphous materials. That is the difference between the crystalline and amorphous materials. Okay, crystalline will be, in case of crystalline materials, so atoms are oriented in a long range periodic order. Okay, so that is the crystalline materials. So here monocrystalline silicon we will use, as well as amorphous silicon material also we can use as a solar cell materials. Next, so compound semiconducting material, that means third and fourth group semiconducting materials. These semiconducting materials generally we will call it as compound semiconducting materials. So for preparing the solar cells we can use so these compound semiconducting material also. So gallium arsenide, indium phosphate, and gallium antimonide, and aluminum gallium arsenide, and indium gallium phosphide, and indium gallium arsenide. So we can use so many combinations also. So that means what is the our main aim is, so to increase the efficiency. So what is the definition of efficiency? What is the definition of efficiency here? So here how much solar energy is incident on here. So so that means how much that energy is converted into electrical energy. Okay, so that means generally last class we discussed about that. So maximum efficiency is up to now 30% efficiency. Okay, if you prepare more efficiency solar cell, means that is more useful. Okay, so for preparing the more efficiency solar cell, so scientists are doing so many combinations, researchers are doing so many combinations of these materials. Okay, someone are using gallium arsenide. If you dope another material, to gallium arsenide, may chance to increase the efficiency, so that's why, so they are using different combinations, to increase the solar cells, to increase the efficiency of solar cell. Because solar cell nowadays, so most what is that encouraging materials are the solar cell materials, because so total future is depends on the solar cell materials only. Okay, so others all sources are not a renewable. Okay, so but only solar energy is the renewable. Okay, that's why, so if you prepare the solar cells, okay, so that will be good, and it is the most research are going on. So mainly nowadays solar cells only. Okay, nowadays solar cells only, everyone trying to improve that efficiency of the solar cell. Okay, yeah, so here different combinations we will use. So here, so for improving the efficiency. Okay, now, so one more thing is thin film solar cells. Thin film solar cells. Okay. Generally used in case of thin films, cadmium telluride. Telluride. Cadmium telluride is so mostly used thin film solar cell, and one more is the so copper indium gallium diselenide. Okay, CIGS, copper indium gallium diselenide. Okay, so this is the so another material used in a thin film solar cells. In case of thin films, how to prepare thin films means, so first of all we have to prepare the solution of cadmium titanate material. Okay, so in that solution is just what is that in my yeah by using different techniques, so we can coat on a one substrate material. If you will take either that substrate material will be either metal or any other, so if you will take the metal substrate and we will dope on that metal, we will just deposit it on that metal substrate. Okay, so that solution will be just coated on a metal substrate, so it will form like a thin film. The thickness is very small. The thickness is very small. It is in micrometer thickness. Okay, so that means so because of these thin films, so we can reduce the quantity of material. We can reduce the quantity of material, and we can increase the area. We can increase the area of the what is that light absorbing area. Light absorbing area. So that is the main use of thin films. Okay, so you can reduce the quantity of material. Okay, how much quantity we are using, we can reduce the quantity of material, and we can increase the area. We can increase the area. That is the thin film solar cells. Okay, generally used here cadmium tellurate and copper indium gallium diselenide. Okay, and then next one is dye-synthesized solar cells. Dye-synthesized solar cells. So we can take by using liquid dyes. By using liquid dyes, so we can prepare here solar cell materials. Solar cell materials. Those are the one type of solar cell materials. And perovskite solar cells. Perovskite solar cells. Here, general formula of perovskite material is ABX3. General formula of solar cell, perovskite materials. Perovskite material is ABX3, where A and B are the cations. Where A and B are the cations. Cations are nothing but positive ions. Okay, A and B are the cations. X3, X is the negative ion. Negative ion. That means anions. Here anions example. What is the examples of anions? So like oxygen, iodine. So these are the best examples. Fluorine. So these are the best example for anions. What is the example for cations? So aluminium, magnesium, sodium. These all are the cations only. Okay. So these are the ABX3 structure. ABX3 structure of materials. Okay. So these material will also act as a solar cells. So perovskite solar material. These materials, these structured material, we will call it as perovskite solar cell materials. So there are double perovskites also there. Double perovskites means, so these ABX3 layer will be repeated again and again. Okay, so that is the double perovskites material. Okay, so these are the perovskite solar cell material. And organic solar cells. By using organic materials, we can prepare the solar cells. That is the organic solar cell. And so one more is graphene solar cells. So by using graphene, so graphene has so the graphene is capacitor. Generally, in case of capacitors, so this graphene will be used. Okay, so because it stores large quantity of charge. Okay, large quantity of charge. Okay, so that's why this graphene also used as a capacitive material, and this also used as a solar cells also. Okay, I will show you some some examples here. See here. So here different types of solar cell will be there. I will explain you. So generally this solar cell material will be like this. Okay. So here that means within the small area there are so many number of junction, that PN junction diodes will be there. So many number of PN junction will be diodes will be there within the small area here. Okay. Within that small squares. So here square like that, in small area there will be squares will be there now. In that squares so many diodes will be array of diodes will be present. Okay. So that is the solar cell structure. If you will take here, so many types of solar cells will be there. So monocrystalline solar cell. Okay. Yeah. So this is the monocrystalline solar cell material. Okay. And the compound semiconductor solar cell materials here. So this is the structure of compound semiconductor material is zinc blende structure. Already we discussed. Okay, here it is given. So how to prepare the solar cell material here. So this is the solar cell here. So uh, it will be instant on the different lights. So indium, gallium, arsenide, phosphate. So like that. So it will be there. Yeah. So this is the structure here. This is the structure of compound materials, compound semiconductor material. See here. So gallium arsenide. So this layer width will be just 350 micrometer, and aluminum gallium arsenide 100 micrometer. Gallium arsenide 3500 micrometer. So like that, by using different structures, here. So combination of different structures also. Okay, combination of different layers also. Here so many junctions will be formed. So here that means generally we discussed only one junction. In one junction electric field will be produced. Okay, so if you will take more junctions means what happens? So in each junction, so there will be electric field will be produced. Okay, if you will take resultant means, so that potential will be high compared to the, so one junction. If you will take multiple junctions, so what happened, that potential will be very high, and we can get more output, see here. See, this is the n-type metal here. That means uh, one, that ohmic conductor, we said that ohmic conductor we will use now. So here we will place here ohmic conductor. So this so p-type metal means this is the another ohmic conductor. Okay, so by using these ohmic conductors, so we can get the output here. Okay, so here there are multiple junctions. So because of the multiple junctions only, we can increase the output power. Okay, so here so many techniques will be there for preparing the solar cell materials. And thin film solar cells. Okay, thin film solar cells. And so this is the thin film solar cells here. Generally we will use here. So which type of material we are using? Okay, so already I said that cadmium, and so another material will be used, and amorphous silicon. Amorphous silicon also will used as a thin film. Okay, see here. So general monocrystalline. If you will take monocrystalline silicon means, so that order. So this is the long range periodic order. Okay, if you will take amorphous, so that order is missing. Okay, this is order is missing, and there is a so many gaps will be there here and here. Okay, so these are the amorphous silicon material. Okay, this is the hydrogenated amorphous silicon material. Okay, and copper indium gallium. So I said that before, so this is the one of the example of copper indium gallium. What is that? Thin film semiconducting material. Okay, so here, so this will be copper, indium, gallium, and selenide. Okay, those structure will be like this. And cadmium titanate. So cadmium titanate structure will be like this. And this is the cadmium titanate material, and dye-synthesized solar cells. Okay, here this is the dye-synthesized solar cells. So whenever light is absorbed, it will what happen? So that electron will goes to the excited state, and that means it will goes to the ionized. It it will be ionized. Electron will goes to the valency bond to conduction band. That means it is ionized. So so because of that ionization process here, what happened? So here accumulated, so holes will be accumulated here, electrons will be accumulated here. Okay, because of that, what happened here? Some potential difference will be developed. Potential difference will be developed. This is the dye synthesized. Okay, dye synthesized solar cells and perovskite solar cells. If you will take, so this is the perovskite solar cells. I told the structure. So this is the ABX3 structure. ABX3 structure is the perovskite solar cells structure. Okay, same process here. Holes, so electrons will jump from here to here, and same process will be occur in that. Okay, this is the, so these are also transparent solar cells. Perovskite solar cells are, yeah, perovskite sandwiched solar cells. Okay, here so different what is that, junctions will be formed here. Because of that junctions, what happened here, we can improve the voltage, output voltage. Organic solar cells, by using organic materials we can prepare the solar cells, that is the organic solar cells here. So this is the, so donors, acceptors. Okay, so he, okay, these are the organic materials, P3HT, PTB, B7, and graphene solar cells. So this is the graphene structure. Graphene structure, this graphene also used as a solar cell material. Okay, so this is about the some different types of solar cells. If you want, means I can post this link here, link to your chat box. So if you want to visit, you can visit. Okay, so different types of solar cell materials here. Okay, so I posted the link. If anyone want to interest, means you can visit that. So different types of solar cells here. Yeah, so solar, these are the solar cell materials, and next we will go to the applications. Applications of the solar cell materials. Applications of solar cell material. First one, applications. In that industrial application, cathode protection. Okay, for protecting the cathode here. So because cathodes means here. So so positive ion. Okay, so positive ion means sodium, aluminum. These all are the cathode materials. So those are chance to oxidize easily, oxidization. Okay, so because of that oxidization, what happened? So corrosion will occur. Corrosion will occur. If you will take iron, okay, so if you place the iron in the outside place, if you absorb some moisture, and so it react with that moisture, and corrosion will occurs. Okay, to prevent the that to prevent the corrosion, so these solar cells are useful. Okay, so and next one, alarm systems. Alarm systems. Solar systems are used to power railway signal alarm systems. Okay, so that if you will take so many railway systems, by using solar panels, so we can use it as a alarm systems. So for signaling and alarms, so we can use it as a alarm systems. And next one is the defense equipment. Okay, so what is the application in defense means? Mobile telephone and remote instrument, etc. Okay, so for industrial applications, these are the industrial applications. And next, solar cells are used in satellites and space vehicles to supply the power to electronic and charge storage batteries. Okay, so this is the application of the solar cells in satellites and space vehicles. Okay, so next, ocean navigation aids. So number of lighthouses are powered by the solar cells. Do you know the lighthouses? Lighthouses in middle of the ocean. In middle of the ocean, there will be some to protect the signaling system. So that means some lighthouses are built. Okay, so this gives the instructions to the what is that, navigators, instructions to the navigators. So uh, for working of those lighthouses, so generally power solar cells are used. Okay, and telecommunication systems, radio transfers on mountain tops or telephone boxes in the uh, count country can often be solar powered. Okay, this is the telecommunication systems. Similarly, next, social applications. So in case of social applications, electric power to remote villages. So PV power water pumps. PV power means photovoltaic power. Okay, photovoltaic powered water pumps, and PV power refrigerators and washing machines, and television and lightning. Okay, so for solar applications, so by using, so we can produce the electric power in remote villages and PV powered water. So PV power means, so by using PV power is nothing but, PV is nothing but photovoltaic power water pumps. Okay, so these are the all are the some solar applications. And solar cells are used to power calculator and watches. So generally, so in our some so many calculators will works as a by using these solar powers, okay. So normal light also it absorbs and it will works. Similarly, watches also there. And solar cells are used to provide commercial electricity. Okay, commercial. So for commercial electricity also we can use here solar cells. Okay, so advantages. So these advantages are we will discuss in next class. So, okay, these are the some applications of solar cells here. Okay, if you have any doubts means you can ask. So first of all, I will take the attendance. So after the attendance, you can leave the class. So first of all, I will take the attendance. You can leave from the class. If you have any doubts, you can ask. Otherwise, you can leave from the session.